Hi, this is Yanling from PolySpeed. Today, I'd like to introduce you a model development and parameter analysis for a evaporative cooling system, which is enhanced by the internally cooled desiccant. Today's presentation will be divided into 5 parts. First, I'll introduce you the background and previous literatures in this field. Second, it's about the model's development and numerical simulation, which is also the methodology. Third is the model validation. And the next one is result, which is followed by the conclusion. Researchers usually spend 8 to 11.5 hours in the office for study and research. A good indoor environment, especially the temperature and humidity, might help to create a comfortable building environment and promote for the work efficiency. Hong Kong stays in a hot and humid regions, where the energy consumption accounts for 30 to 50% is consumed by traditional air conditioning systems. To be worse, the high temperature and humidity environment might cause a growth of the bacteria, fungi, and virus, especially in today's pandemic world. Therefore, it is very important to use some new facilities which is in high energy performance other than the traditional MVCR system in Hong Kong. For cooling, EC is well recognized for effectively handling the sensible heat load. And to deal with the latent heat, the liquid desiccant dehumidification stands out as an effective technology. So, if those two components combine together into a system, it might achieve free of harmful CFC-based refrigerant and have giant cooling potential. Shown here is the newly proposed internally cooled desiccant enhanced evaporative cooling system model, which is also the ICD-VAP system. In this system, the application of return air will be optimized. Here is the indirect evaporative cooler, where it is well recognized to have effectively handling the sensible heat load and apply the principle of the evaporative cooling. It can utilize cold and dry air from the inside to return to the secondary channel to be evaporatively cooled again, that is to become an IEC. However, due to the high humidity environment in Hong Kong, it might have an effect on the cooling capacity, and high humidity area might not have sufficient condensation and dehumidification for pure IEC. Therefore, it is important to use a dehumidifier, such as traditional adiabatic liquid desiccant dehumidifier, LDD, as can be shown from figure 1. The inlet air gets into the dehumidification channels to have a dehumidifying process, where the desiccants, such as lithium chloride, absorb the heat and at the same time absorb the water and release the heat to the air. They're facing one challenge is the deterioration resulted from the solution temperature increase. Therefore, it might use an internal cooling, such as indirect evaporative cooling, assisted to LDD. As can be seen from the bottom of this slide, there has added one evaporative cooling channel between the dehumidification channels, where they use the exhaust air from the room as an inlet air get into the channel to have an evaporative cooling process. Therefore, the first potential improvement for LDD might be added an internal cooling. And for another improvement measures for LDD might be from the flow patterns. Here shows 3 traditional flow patterns, the parallel flow, cross flow, and counterflow. Researchers find that the counterflow has the best dehumidification performance and heat exchange efficiency. However, it is not conductive to insulation. And for cross flow, it might have better heat exchange efficiency than parallel flow, and it can have lower pressure loss. Therefore, why don't we combine the counterflow and the crossflow benefits together, like we use a hexagonal plated heat exchanger? That means to have the crossflow on both ends, to have a better convenient insulation and lower pressure loss, and have counterflow in the middle to have a better heat exchange performance. Therefore, in this study, there will use the regenerative IEC and hexagonal internal cooling LDB to optimize return air ratio and energy saving performance. Next is about the model development. Figure A and Figure B shows the schematic diagram for LDB and RIEC. For LDB, there has arranged the water and solution nozzles at the top. And in primary air channels, the primary air have a dehumidifying process with the spread solution, while the secondary air has the indirect evaporative cooling process. For Figure B, in RIEC, there also have an evaporative cooling process in the secondary channel. And for primary air, it can be indirectly cooled by the secondary channels. Therefore, by discretizing the differential term into algebraic form, a two-dimensional finite difference model can be established. This model is based on several assumptions. First, the airflow is fully developed. The unit is adiabatic. The heat and the mass only transfer vertically through the wall. And fourth, the Lewis number is uniform. Here shows the governing equations of LDB. It can be divided into primary channels and secondary channels. Here shows the moisture content change and enthalpy change, and also the energy and the mass conservation equations of different channels. The numerical simulation of LDB is also shown here. Here calculated the heat exchange Q between the channels and the total heat transfer coefficient and the thickness of the film is obtained. Based on the above equations mentioned, the governing equations can be achieved. For primary channels and secondary channels is shown here. Here shows the numerical simulations for RIEC with the governing equations and numerical simulations of primary and secondary channels. It starts from inputting the parameters and adjust the assumed water temperature and secondary air temperatures and moisture content. It can calculate along the IEC-assisted LDD module and the RIEC module. If it is converged, we can print and output the result. And also, the outlet air can be reused, can be sent into the indoor thermal and the mass process. The exhaust air can be reused in the LDD module. There has data on max sensibility analysis. We'll find the best number of grades is 70. Third is the model validation. This model has been validated experimentally. Here shows the test rig, where the primary air gets into the LDD and then transformed into IEC. The outlet air in the indoor simulator have a mass and energy process, and the exhaust air can be reused into the LDD's internal cooling channels. This model has been validated, and the deviation between the experiment result and the simulation result is less than 20% in very different input temperature, relative humidity, and the solution concentrations. Therefore, this model might accurately predict the system. Fourth is the result. First, first result is about the influence of RC in outlet temperature and humidity ratio. RC is the return air ratio from the room to the LDD. It is also the secondary air to primary air mass flow ratio in the LDD. The result can show here. The larger return air ratio can bring better cooling effect. In general, the larger the ratio of RC, the better the dehumidification effect of the dehumidifier. If we comprehensively consider the cooling and dehumidification performance and guarantee of air supply air volume, when the return air ratio is 0.3, the overall effect of the system is optimized. Second is about the air handling process of the system. If we using the model developed above and the simulations carried out at typical design air conditions in Hong Kong, the ambient air first dehumidified in the LDD unit to remove latent and partial sensible heat, and then cooled by the RIEC for sensible load before entering the room. The air conditions of each point in the psychrometric diagram referred to table 1. Third is the energy performance of the system. For the DEV AP system, the total cooling capacity can be achieved at 7.76 kilowatts, and the energy consumption is estimated to be 0.9 kilowatts. The COP is 8.6. For MVCR system, if it is estimated COP to be 4, the energy consumption of the traditional MVCR system is calculated to be 1.94 kilowatts. Therefore, the newly developed ICDEV AP system is 48% more energy efficient than a conventional MVCR system. Here shows a discussion about whether we can directly transform the exhaust air to LDD and using the RIEC, or design the system as the exhaust air partially used in LDD internal cooling and partially used for IEC. Result shows on the figure B. As can be seen, the regenerated air brings higher evaporative cooling potential to secondary air, while it might sacrifice some air volume sent into the room. So if the air volume can meet the needs, if RC is larger than 0.8, the energy performance of the air directly is transformed into LDD and using RIEC system can perform better. Here is the conclusion. In this study, this system has used the regenerative indirect evaporative cooler and using IEC assisted for the liquid desiccant dehumidifier. This system's model has been validated experimentally. There have studied the optimization return air ratio and the energy performance. Here are some main results. First, the optimal return air ratio is 0.7, and COP is 8.6. The newly developed system versus traditional MVCR system, the energy saving rate is 48%. Last one, I'd like to appreciate the support from UGC FDS and IDF. And thank you so much for your listening.